Okay, looks like the line has ended, so we can start, and we have a full house today, partly because of the Heidelberg Harvard conference taking place, but just the other part is that it's an exciting forum, and we have good talks today. So, we just held an excellent ITC colloquium by Diederik Kruijssen. Did I say it right?
Excellent.
Okay. Half of my genes are German. So. But,
that wouldn't help.
And we look forward to hearing more from him. Actually, one thing that you said that I didn't like was that we have to pay more attention to observers. Well, I agree with the general sentiment that data, guides the progress of science. But every now and then, we should sit in our offices and think about a problem hard and try to solve it before the observers, so that we can guide them. And half of the Nobel Prize this year was awarded. Half of the Nobel Prize was awarded to a theorist.
I'm trying to spread my chances.
So we are starting today with our own graduate student, Ana-Roxana Pop, that will talk about theoretical predictions, right? Yes. X-ray and Sunyaev-Zildovich scaling relations in IllustrisTNG. And then we move on to David Zinn, who is giving the CFA colloquium. Where is David? Over there. He's visiting us from Johns Hopkins, and he will tell us about the Hubble NUV-Optical Exoplanet Spectroscopy with peak 3 UVIS. He will explain all these acronyms, right? Sure. Yeah. Some of us are theorists and do not know them. And then we'll hear again from Diederik, who will speak about globular clusters, revealing the formation and assembly history of the Milky Way. And we'll conclude with our own Shmuel Bialy, who will tell us about cold clouds as cosmic ray detectors. Anna.
Thank you for coming, everyone. Today I will tell you about work that I've been doing as part of my PhD here, together with my advisor, Lars Hernquist, David Barnes, as well as the IllustrisTNG collaboration. We will look in particular at the hot gas at the centers of halos, both clusters, groups, and galaxies, and the X-ray emission, as well as the Sunyaev-Zildovich effect, or the SZ effect, for these objects. And the reason we look at these properties of the gas, for instance, the density, X-ray luminosity, and the temperature, is because these properties are highly sensitive to what happens with this supermassive black hole at the center of the halos. And in particular, when it comes to simulations, we can use these gas properties as a way of probing whether the AGN feedback models that we implement give us results that are similar to what we expect from observations. Many of you might be familiar with Illustris and IllustrisTNG. Those are cosmological simulations that look at the evolution of baryons in galaxies across cosmic time. And Illustris, in particular, has had a lot of success at reproducing many of the observables in our universe, but didn't do so well when it comes to X-ray. So here I'm showing the X-ray luminosity in the soft band along the y-axis as a function of the total mass enclosed inside of aperture of R500. This is the typical aperture I'll be using because we talk about X-ray observations. Here, the observations are shown as the gray points in the upper right corner, and you can see that they follow a somewhat straight line trend. But when it comes to the Illustris halos, which are shown in red, you can see that they lie way below observations. This is because the AGN feedback in Illustris was too strong, and it was driving too much of the hot gas away from the centers of clusters and groups. To start on a happy note, when we move on to the next generation of simulations, which is IllustrisTNG, here is shown with the blue points, you can see that we lie a lot closer to where the observations are. And I'll emphasize this is the exact same simulation box size of 100 megaparsec on a side. So many of the points in Illustris actually were lying below the limits of the figure I was showing here. Another big advantage of the IllustrisTNG simulation is that we have this larger simulation box now, which is 300 megaparsec on a side. You can see them in the upper left corner. And the halos coming from that simulation are shown in orange here. You can see that we not only come quite close to observations, but we have much, much better statistics, and especially in an area where the observations that we have so far are. So in particular, we have over 150 clusters that are above 10 to the 14 in solar mass in M500. And with upcoming surveys, both Rosita, but also SPT, Fuji, CMB Stage 4, the Simons Observatory, we will have a lot more clusters to fill out the observational space, but also lower mass objects, like groups and galaxies. And I have to say here that a lot of the work in the literature stops at doing this sort of scatter plot and saying whether or not the simulations are in reasonable agreement with the observations. But there's a lot more information than just using a simple scatter plot. In fact, if we look closely at the medians, we see that we are still about 10% off. It's a great success compared to Illustris, but there are still differences between the simulations and the observations. And then it's worth asking the following question. Is the remaining difference simply because we oftentimes do not compare apples to apples when it comes to simulations and observations? Or is there some more underlying physics that we're missing in our models? So in order to answer this question, together with David Barnes, I've been working on an X-ray pipeline where we try to apply techniques that are closer to what is being done for observed data. So just in a couple words, we compute a mock X-ray spectra for each of the gas cells in our halos. We then follow up by computing the spectra that you would get for each of the individual elements that are being tracked in TNG. We sum up the emission in radial bins, and we, of course, take into account that whether you use one survey or another, you might get slightly different effects. So we include the energy resolution and the effective area for your survey of choice. Our choice has been Chandra for the following figures. Last step, we fit a single temperature template for each of those radial beams, and that is the observed estimate of the density, temperature, and metallicity of the gas as a function of radius. It's a lot of words, and this is a short talk. So the main two takeaways, the two factors that make the biggest difference from the simple, naive initial output of the simulations. One of them is the emission lines. Especially as we move from clusters to groups and to galaxies, the emission lines start to enter the soft band X-ray spectrum, and they drive the luminosity higher. So the orange line you see tells us that the effect of the emission lines is important, and in fact, an object with a mass of 10 to the 13 could end up having a luminosity even double than that of a simple naive estimate. The second big factor is that observers, of course, don't have access to the full 3D shape of each of these objects. So they have to estimate what is R500. So if we take into account the bias introduced by that, and by bias I mean in this case the ratio between a spectroscopic estimate of the mass, the X-ray estimate of the mass, divided by the true M500 that we get from the simulation, not only that you see a bias, which is the fact that these observed points are below the line that marks a ratio of 1, but you also see a huge amount of scatter. And those are the blue contours that you see indicating 1 and 2 sigma scatter. These have important effects, especially for precision cosmology, if we want to use it for that, but also in terms of shifting our results a little bit, but also introducing a lot of scatter. So here I'm showing in blue the results for the luminosity as a function of mass. In magenta, you see what were the previous results when we were measuring things inside the true aperture from the simulation. You see the medians shift a bit, but most importantly, we now recover a scatter that is similar to the scatter that's seen in observations. So a lot of the scatter that you can see in the observations is actually caused by these estimated masses. This is what's driving the blue line at the bottom of this figure to be somewhat closer to observations. Okay, but what about self-similarity? As you've seen on my previous plots, we are interested not just in clusters, but also smaller objects. Self-similarity tells us that all we need to know about an object is the mass of the object. The bigger the mass of the object, the luminosity should be proportionally bigger. The smaller the mass, the luminosity should be smaller. And that holds for a bunch of other X-ray quantities, as well as the YZ parameter, for instance. But self-similarity, which gives us a simple slope on a log-log plot, actually depends on several assumptions. One of them is that our objects are in virial equilibrium. The other one is that feedback processes are negligible. And that is not the case, especially as we move on to smaller objects. Here I'm just showing a bunch of the scaling relations, and you see that a straight line is not a good fit. And more importantly, especially as observations will let us probe beyond smaller masses than just clusters in the upcoming future, we have to be careful, because where you set the limit in mass for your sample will determine the slope that you'll get. You will no longer probe the true slope of the clusters that might be self-similar, but rather be contaminated by smaller mass objects in your sample. So I propose that it's time to no longer use a straight line in order to fit this data. And neither should we go to a far too complex model, but for now, a model that I think can be easily adopted both by observers and people who work with simulations is a smoothly varying power law. I'm just using a hyperbolic tangent that allows me to transition from one slope that characterizes the very high mass objects, some of them that maybe I'm not even having in my current state-of-the-art simulations, but we might have several years down the line. A different slope, alpha 1, that characterizes smaller mass objects, and also a location for the pivot. Where this break in self-similarity happens is very important because it tells us more about the AGN feedback. And not only where it happens, but also the mass range over which it happens. What we've seen in astrophysics oftentimes is that no process happens very sudden, especially when it comes to hundreds of thousands of galaxies. Instead, the transition happens smoothly over a mass range that we want to characterize. So this is the model that we use and that we fit both the relaxed and unrelaxed cluster. We find some interesting trends. One of them is that the slopes tend to be, of course, shallower as we go to higher masses. We also find that for relaxed clusters, the slopes are steeper. So here is the red dotted line that you see on the right side that is significantly steeper. And even if by eye, maybe you would think the left fit is good enough, if you look at the actual slopes, the differences are huge. So between a 1.9, that would be the prediction of a single line, to a 1.4, roughly, slope if you move to the highest mass clusters with a smoothly broken power law. So this has been in luminosity, but we apply it to all the scaling relations. I'll show you what things look like for the Y and Z parameter. On the left column, I'm showing you the true aperture. On the right, I'm showing data where we use the X-ray estimated masses. And you see quite a big difference between the two. The slopes are different. At the top, you see the single power law fit. And here I go down to 10 to the 12 in M500. So quite small galaxies when it comes to the Y and Z parameter. And this really allows us to see that there is a break in self-similarity. And this will be important for cosmology. Moreover, these shaded regions now will indicate to you by eye where this transition happens. And in the bottom panel, I'm showing you how the slope evolves according to our model between the two alpha 1 and alpha 2 slopes that we estimate for very low masses and very high mass clusters. Interestingly enough, it's only this red line for relaxed clusters that tends to go to the self-similar prediction of 1.66 for the slope, versus the other unrelaxed sample tends to have a lower slope for the highest mass clusters. Finally, another way to probe what happens with AGN feedback and how that influences the scaling relations is to look at the redshift evolution. So here I'm showing the Y and Z parameter once again as a function of mass, but the different colors indicate different redshifts. And you can see that at the galaxy scales, the Y and Z parameter decreases slightly as we go to lower Z. And here I am correcting for what you would expect to be just cosmological evolution itself. And one last comment is that we also see lower scatter as we move to higher masses, as well as higher redshift. So I'll leave you with my conclusions, and thank you very much for listening. No, I would say that the AGN feedback still has an important contribution. It's just that we see how AGN feedback changes in the way it affects the X-ray gas, whether we are at high masses or low masses. So when we see the break, it's not so much that AGN feedback becomes important, but rather that the nature of the AGN feedback changes. And the slope that you get, even at high masses, will be affected by the strength of the AGN feedback.
Okay, so much of the agreement in data and simulation is due to the fact that you incorporate the correct AGN feedback, so to speak.
Yes.
Otherwise, you would get the wrong answer.
Yes, but the question can also be inverted to ask what can we learn about the nature of AGN feedback by applying this method to observations.
So if you plot YSZ versus Y sub X, then there's so this is all observational, you get a scatter that is a combination of the intrinsic real world scatter plus observational scatter. How does that scatter compare to the scatter in your models?
Yes, so what you're mentioning here is YZ versus YX, which is the product of the gas mass and temperature. And indeed, YX is well known to be a lower scatter measure out of all scaling relations, similar to YZ. So YZ versus YX has relatively low scatter. That's why it's very good for cosmology. When we apply our method, we find, again, reasonable scatter compared to observations, but overall lower than you would see in luminosity versus mass or temperature versus mass, as you would expect.
So it's comparable.
Yes. So the mass bias and the scattering the mass bias is one of the major factors.
So when you calculate something like an emission line spectrum, which depends on metallicity, where does that metallicity come from?
So we do track 10 different metals in IllustrisTNG. So we have access to those, but we don't take those to be the underlying truth a priori. So we still both the metallicity, the density, and the temperature for each of those gas cells, we are running them through the pipeline so that we get what the observers would see to be the metallicity in each of the radial beams. But we have information for each of the gas cells in the simulation.
And you do get the third solar fraction of the solar metallicity.
Yes, so running the pipeline doesn't change the average metallicity significantly.
Any other questions for Anna? If not, let's thank her again.
All right, can people hear me? All right. So what I wanted to share with you for this lunch talk, for the colloquium, I do exoplanet spectroscopy. I'll get into how we do this sort of work and so forth. But I wanted to share some ongoing work, sort of a new mode on Hubble, which is the ultraviolet UVIS spectroscopy. So in the exoplanet field, over the last 5, 6, 7 years, the wide-field camera has really revolutionized this field with infrared spectroscopy, and now we've detected water in exoplanets from Jupiters down to sort of mini Neptunes and probably like at least 40 planets. But there's a less known mode, which is the ultraviolet infrared spectrograph, which is the ultraviolet side to that same wide-field camera 3 instrument. So myself and a lot of others, when this sort of came online, looked, oh, there's some spectroscopy you can do with this spectrograph. But when you kind of look at the details, I think everyone was kind of scared and basically stuck to what we knew, which is COS and STIS, which are great instruments. And you can sort of see what the spectra looks like down here. You have overlapping orders, you have curved spectral traces, and all of these things are a pain to deal with, and everyone said, let's not deal with it at all. And basically there's been no science with this done ever since Servicing Mission 4, which has been years now. But we're gonna have to deal with this one way or the other with James Webb, because there is this JWT SOSMO. This was built to do exoplanet transmission spectroscopy, and lo and behold, it also has similar dispersed overlapping orders. And so now you can imagine, oh, we're going to have to deal with extracting our transit spectra to X number of parts per million and deal with overlapping orders and so forth. So there's a real push to figure out, okay, how do we deal with overlapping orders with space-based data? Can we really extract spectra at the parts per million sort of levels that we need, to do sort of the next generation great work? So this sort of spurred sort of a test program to try this out, basically. So here's sort of what we proposed to do. So this was 10 orbits on a planet we already looked at, or we're already looking at, which is HAP-P41. This is a hot Jupiter. And there's already been a detection of water in the near infrared with the UVIS, and you can see the water feature right here, which is muted. And there's seemed to be sort of a hint of a slope, which could be sort of from clouds or aerosols in the atmosphere that cover it. So one reason you want to look in the UV would be to get a handle on those scattering particles. So UVIS has a spectral range all the way to 0.2 microns, 2,000 angstroms. So at these very small wavelength, short wavelengths, you can really get a handle on small particle sizes. So even with just a few data points in the UV, you could really say something about, for instance, how high these aerosols get, maybe up to 10 to the minus 6 to the negative 6 bar in this sort of simulation. So this is what we expected to get. But also, there was planned STIS data too, because whenever you work with some sort of new mode, how do you know what you're actually getting is realistic? We don't have a lot of calibration for this. So what we did was calibrate it against other data. We've used STIS now for hundreds of orbits, and we know the instrument quite well. So we wanted to compare the UVIS data we got to the STIS. If we get the same answer, that we have confidence that things are making sense. So, and when you look at the UVIS in more detail, actually there's quite a good reason you might want to use this mode. Here is the throughput of UVIS, the G280, compared to STIS G430L and just G750L. These are the low resolution spectrographs in the optical. And you can see the throughput is very high. So up to 30% here at about 2,500 angstroms. And even in the optical, if you combine the plus and minus orders, which is here's the plus order and here's the minus order, these two together, you actually get higher throughput than the G430L, because especially this poor STIS has been in orbit for now decades and is slowly degrading, so the throughput isn't nearly as high as it used to be. So in principle, you can get much, much better spectrophotometry with UVIS. And if you compare it, it's almost as high as these nice infrared channels.
Sorry, can you just tell us what you're looking at those images? I mean, one axis is wavelength and one axis.
So this is wavelength. So here's this is the dispersed spectra. Right. So here is, this is sort of the UV end, and this goes all the way to the infrared. And then here's the second order here. And then here is the minus order of the spectra. So, and this is the zeroth image. So here's the
And the other axis is space.
yeah, so this is space. So it's a slitless spectrograph. So you see one star here. This is HAP-P41. And then there's the dispersed spectrum of it. And it also has a companion star below here. And you can see the spectrum of the companion star on both sides. So this is another challenge. It's slitless spectroscopy, so you have to worry about overlapping spectra and so forth, and background, and other features why, which are reasons people haven't used this mode. And
What was the difference between the original and the clean? From here, it doesn't look like they're very different.
oh, well, so when we got the data, it turns out like the hard parts for using this mode are sort of things we kind of take for granted, like subtracting cosmic rays. That's sort of a zeroth order pipeline thing that you just push a button and the cosmic rays come out. But there's a lot of cosmic rays because the wavelength range is really large. You go into the UV, and lots of cosmic rays hit right on your spectra. And when you're trying to do a few parts per million, you have to really worry about that. So just extracting the spectra, dealing with the overlap, and then cleaning that, is non-trivial actually, and it's been, difficult to work with, especially with. It turns out there's virtually no calibration that's been done with this instrument from Space Telescope. There's no pipelines to go and download.
Sorry, did you know that this is exactly the same what we have in Chandra for the spectroscopy?
Sure, yeah.
So if you be in touch with the MIT people, they'll tell you how to do this analysis.
I mean, we've been doing this with other spectrographs, so it's just a matter of applying those same techniques. So yeah, it's. So here's the transits we get out. So we have 2 visits, and here's one of them. So because you get the plus and minus orders, you sort of get 2 transits for the price of 1, 2 spectra for the price of 1, which is great, because now you can compare multiple things. Here I'm showing, here's the raw data on the bottom here, and then you can sort of see the transit in the middle, and then you have to correct that for these systematic errors. So essentially what happens is Hubble moves slightly during the transit, during the orbits, and that changes the photometry very slightly. So you have to correct for that. But it turns out that the level of those systematic errors is actually quite small compared to what we've seen with other data sets. STIS, for instance, which has very large breathing trends, it has lots of slit losses, and even the wide field camera infrared has lots of charge trapping, which leads to very large ramps in these sort of light curves. So it turns out already the systematics are much less, and even in this field, we often throw out the first orbit because it has such different systematics, it's very hard to correct. But for UVIS, we haven't had to do that. We can use the whole time series, in this case 5 consecutive orbits, to do the spectroscopy. And basically, we've achieved already great precision. Here's a transit depth measured to 58 parts per million, and the plus or the minus 1 order, which doesn't have quite as high throughput, you get 88 parts per million, and this is on a V of 11 magnitude star. So the trends are actually fairly small, and what I've used is a new technique called jitter detrending, which basically just takes the spacecraft pointing and then detrends these sort of changes in the photometry for that. So here's the spectrum we get out currently. So the UVIS is in black, and then our STIS data is in gray here. And it turns out, so if you go on this STIS website, or its SDSCI website, you'll basically see plots that go to about 0.4, and that's where you start to have overlapping orders and so forth. But it turns out you can get data all the way from 0.2 to 0.8, and the errors are actually very good. And we get combined white of the 2 transits, an error of about 35 parts per million, which is about as good as anyone has done on Hubble so far. So keep this mode in mind going forward, because it turns out this is a great instrument. Yeah, it turns out some of these bumps and wiggles are interesting, but that's in progress.
I have a question about the jitter model.
Yeah.
How did you do it? It seems like on the time period, it's like the parts are coherent on some time scale. So I just wonder, maybe it's part of the model.
So the jitter detrending, Hubble records the exact position of the reference stars. To actually, sub-pixel. I mean, this is how it points to sub-pixel levels. So during the time series, when the spacecraft is moving at this sort of level, and you can sort of see it in the light curves as it changes up and down, this is often very repeatable, because just the way that the breathing on Hubble works. So one orbit to the other, this way you see these little waves, and you'll see that in the pointing where it's kind of, drifting in a similar direction. So with jitter decorrelation, it's using that position information, which is then it is repeatable, basically orbit to orbit, and then corrects for it that way. Yeah. Thank you.
Okay, good. I'm interested in how stuff in the universe formed. And I guess that's something that we all have in common. But what it does for me is I just gave a talk during the ITC colloquium about star formation, the molecular cloud life cycle, and galaxy formation. But I have another passion, which I'd like to share with you right now, which is how we can use globular clusters to learn something about high redshift star formation and the formation and assembly history of the Milky Way. And this is a sneak preview of a colloquium I'm giving at MIT next week. Now, I realize most of you probably don't go to MIT colloquia. So I hope maybe I can convince some of you to join. So what you see here is a galaxy formation simulation, a zoom-in simulation of a Milky Way mass galaxy. And all of the dotted dots that you see moving here are globular clusters in this simulation. And they're color-coded in this case by their metallicities. And this is part of the eMosaics project. And this is a project that we've been developing in Heidelberg and in Liverpool, which basically uses the Eagle high-resolution volume, which is shown here in the dark matter, and re-simulates the 25 Milky Way mass galaxies within this volume with a complete model for the formation and evolution of the stellar cluster population within those galaxies. And this is all done using subgrid recipes that are based on what we know about cluster formation and disruption in the local universe. And then basically applying that in a cosmological context with the goal of testing, are globular clusters the regular products of star formation just occurring on the high redshift conditions? So can we try and understand the formation of globular clusters and young clusters in the local universe using the same physics? And just to illustrate, you can zoom in, and this is a little bit of a small panel, but what you see here in different colors is we can track exactly which clusters formed in situ, which clusters were accreted, and which clusters are currently still part of satellites being stripped. So this is really a way of trying to compare to the new generation of observational data with Gaia and LSST soon to try and figure out how to do galactic archaeology in the halos of Milky Way, Andromeda, and so on. And then we follow all of that as a function of cosmic time. So basically how eMosaics works is it uses exactly the Eagle physics. So we run at the highest resolution of Eagle with exactly the same baryonic physics. But then on top of that, we add this model for globular cluster formation and disruption. So we use the hydrodynamics, the local ISM properties, and the local dynamical environment to motivate exactly what fraction of the star formation goes into bound stellar clusters, what their initial cluster mass function is. And all of that we use then as initial conditions to then evolve according to the local tidal field that we get out of the simulation as well. So we self-consistently track the tidal field tensor for every cluster. So here's shown as a function of look-back time, something called the tidal heating parameter. This is basically the total energy injected by tidal perturbations, by tidal shocks. And you see here a lot of substructures. So this is just shown for 3 different clusters. And here in this box, you can see just the time resolution at which we're following these tidal histories. And all of those wiggles are interactions with substructure in the local environment that each impart further mass loss onto those clusters. So this is just showing 3 of them. Every galaxy that we simulate has of the order millions of those clusters that we all track at this resolution. So this is something you need to do on the fly. So taken together, as I mentioned, that gives us 25 Milky Way-like galaxies that we trace. In addition, we've done hundreds of simulations where we basically try to vary the subgrid physics to see exactly which elements we can trust and which ones we can't. And the 25 that we're left with in the first bullet here are the ones that we end up trusting. Then in addition, we've now run a 34 megaparsec periodic volume using exactly the same physics and at the same resolution, which you see here in the bottom right. And this now contains 1 Fornax cluster, so we can actually really go up the mass scale, and of the order 80 Milky Way mass galaxies. So we can start to do statistics and really track how assembly history affects the properties of the globular cluster population, which you can then invert and say, okay, given a certain globular cluster population, what does that tell me about the formation and assembly history of the galaxy? So I want to share two main results, and one briefly and another one that I'll go into in a little bit more detail. And the first result of e-mosaics is, yeah, it actually works. So we get globular cluster populations that are consistent with what we observe using the physics that are normally used to describe the formation of young clusters in the local universe. So what e-mosaics reproduces, it reproduces young cluster populations, so the fraction of star formation we see occurring in bound clusters in the local universe and how that varies with environment. It reproduces the initial cluster mass function, also the H distributions that we see nearby. And H distributions are important because these are tracers of how quickly you drive disruption in your cluster population. Then in addition, as I mentioned, we reproduce most of the properties of old globular cluster populations. And this is work that Marta Reina Campos and Sebastian Trujillo Gomez, who are PhD student and postdoc in Heidelberg, have done a lot of work on. So, for instance, we reproduce the number of globular clusters per unit galaxy mass, or stellar or halo mass, so these scaling relations, specific frequencies, and so on. We reproduce the radial density profiles, kinematics, H metallicity distributions, I'll come back to that one, but also the high mass end of the globular cluster mass function and the low mass end of the metallicity distribution. These are selective statements, means we don't reproduce the complement of that statement. And there are reasons for that I'm happy to discuss with you further. Okay, so the second result is that indeed, this idea that you can trace galaxy formation and assembly with globular clusters is no longer just a promise, it's actually something we can do quantitatively now. And I'd like to illustrate that with the H metallicity distribution of globular clusters. So this is shown here now with age or look-back time, and then metallicity is FE over H for 6 different of our simulations. The dots are the globular clusters in those simulations, and they're color-coded by the galactocentric radius at redshift 0. And the contours in the background are the field star population. So basically what you see is that globular clusters trace the moments of intense star formation in the host galaxy. So whenever there is a lot of field stars formed, you also get globular clusters. But what you also see is that there are considerable differences between these 6 different panels. And these differences trace differences in the merger and assembly history of the host galaxy. And that is interesting because it means you could use quantitative diagnostics of these diagrams to try and infer exactly how the host galaxy formed. And specifically, if you look at a given redshift, so let's say here, you take a slice, given a look-back time, you see a range in metallicity. And because of the galaxy mass metallicity relation, the low metallicity globular clusters formed in lower mass galaxies than the high metallicity clusters. And what that means is if you learn to read this diagram, you can figure out exactly which galaxies those globular clusters came from. And that's what I'd like to show here. So this is zooming in on just one of them. So in principle, what you can do is you can draw sort of a vertical line here, but then you see in addition a branch coming off. And this is what we call the main branch. So we expect those clusters, because they're the most metal rich, to have formed in the main progenitor, to have formed in situ, and those to have formed from inaccreted satellites. So what you can do now, because it's a simulation, you can overplot the merger tree in this plane and see that indeed, we see the main branch, the thick line going up here, and here these are satellite galaxies that eventually end up merging at around redshift 0. So we see that this idea actually works quite well. And you can do more. So you can ask the question, at each age metallicity coordinate, what is the typical mass of galaxies forming stars at that coordinate? So let's say 10 gigayears ago, what was the mass of galaxies forming stars with a metallicity of -1, of the order 10 to the 9 solar masses? Now what I'm overplotting here is all of those globular clusters in the simulation again, and these are not open symbols. They're actually color-coded by the mass of the host galaxy that they formed in. And the fact that that agrees reasonably well with the color you see in the background means that you can use this background image to figure out for clusters what the masses are of the galaxies that they formed in at that time, and maybe use that to reconstruct the merger tree. So this is now showing the globular cluster population of the Milky Way on top of this diagram. And basically by taking the colors that you see in the background, you can then infer exactly what the mass growth history was of the Milky Way, but also what the mass growth histories were of the satellites that the Milky Way accreted. Right? You see this exact same sort of satellite branch coming off the main branch here. And that is something we did last year. So here you see the stellar mass growth histories inferred from the galactic globular cluster population, here for the Milky Way, as well as 3 satellites that are implied by the existence of that satellite branch. And what is interesting is that in terms of the median properties, the Milky Way is very normal. It's just typical median Milky Way mass galaxy. But if you look at the growth rate, basically how quickly the Milky Way grew in mass and enriched, it is sitting sort of in the 1-2 sigma regime of Milky Way mass galaxies in the E-mosaic sample of simulations. So what we did with that is we reconstructed the merger tree. We inferred that the Milky Way must have undergone of the order of 15 mergers, and we identified 3. The first one was easy, it's Sagittarius. We know that that exists, so that was not very difficult. The second one was the globular clusters that were formerly associated with a ghost that people used to call Canis Major. Has since been identified as Gaia Enceladus. Helmy had a Nature paper on that. I think Myung was actually the one who discovered it first and who should get credit for that discovery. But the interesting thing here is that we actually predicted this. This was submitted before Gaia DR2, so we were very happy when it was actually found. But we predicted another galaxy, this one, we called Kraken, and we argued at the time that it must have had a similar mass as Gaia Enceladus, and it wasn't found yet at the time. There's now a paper that came out a couple of months ago by Massari, who looked at basically the orbital properties of globular clusters around the Milky Way, and identified 5 specific galaxies that we can, or groups of globular clusters that we can connect to certain galaxies. This is what we would argue is Kraken. They don't think it is. But we now know it is. And the reason is we trained a neural network on the E-mosaic simulations to figure out the initial masses of the galaxies based on the orbital properties and age metallicity distribution. And the Kraken mass that we get is actually very similar to the one of Gaia Enceladus, also very similar to Sagittarius. But it accreted super early. It accreted at around redshift 2, which means that at that time, the Milky Way had a very low mass, which makes Kraken the most major merger that the Milky Way ever experienced. So that's the PR tagline that we're going to go with. And this is the updated merger tree. So we've got Kraken, the Helmy streams and Sequoia, accreting at some point, Gaia Enceladus, and then Sagittarius at the present day. And I'll stop there. Thank you very much for listening. Yes.
Where major dark matter streams should be, or hello stars.
I completely agree. Of course, the slight subtlety is that globular clusters undergo dynamical friction, so they sink in, which means they don't trace exactly the same distribution as the dark matter. But in phase space, that's absolutely true. Yeah.
Do you get a correlation between the number of globulars and the mass of the central black hole galaxy?
Yes, but by implication, we must get that right, because we get the correlation right between the number of globulars and the halo mass of the galaxy and the stellar mass of the galaxy, right? So it's not clear in which direction the causality runs, and probably a black hole doesn't define the number of globular clusters, but yeah, by implication, we get it right.
Comments, questions? Yes,
I don't know if you've seen, but a few years ago, Rafael Dabrusco, who may or may not be here, I don't know, is been studying the 2D plane of the sky distribution of globular clusters and how that differs from a smooth distribution. And we find in Virgo there is a lot of this.
Yes.
Is that type of data useful in terms of your simulations?
Extremely, and in particular in the context of the volume that I showed at the beginning that we're currently running, or have run, so this one here. So I don't have that movie here now, but we actually have a version of this where you see globular clusters trace the cosmic web, but then also within galaxy clusters you see basically fossil streams, because the dynamical times are so long, that persist over very long time scales, and actually using that type of data to make that connection and reconstruct the assembly history of galaxy clusters, I think is super promising.
So we should talk. Are you going to be around for a while?
Till Friday next week.
Okay.
Look for it. Thank you.
So something good came out of this. Well, let's thank Diederik again.
The mic.
Yes, you can have the microphone.
I can. Thank you.
I'm not going to present yours.
Yeah, no, it can help.
No, I think you're better at that.
Thank you.
Cheers.
Okay, can you hear me? Can you see me? Can you see my computer? No. Oh, yeah. Okay.
So this was my original title, but given the cold weather, I decided to switch and to talk about something warmer and talk about turbulence instead of cold clouds. I'll mention briefly this other project, cold clouds as detectors of cosmic rays. But now I want to concentrate on this topic, which I think is a nice combination of two fields: the study of turbulence in the interstellar medium and the chemistry, astrochemistry, study of molecules. This is a talk I gave here at the Harvard Heidelberg meeting, so most of you weren't there, so I guess that's fine. But for those who were, I'm sorry for this. So this is based on two papers, one of which is quite recent, with my collaborators Blake C., who was here, Emil Sternberg, my former PhD advisor, and David Neufeld and Mark Wolfire. And let me start first just with the general idea. So the idea, we know there's turbulence in the ISM. The ISM is highly turbulent. We know it from many observations. I won't get into this. We know that turbulence must play a very important role in regulating star formation in galaxies. Now, another thing that turbulence does, when the turbulence is supersonic, it becomes compressible. So it induces density fluctuations, shaping the density structure of the interstellar medium. On the other hand, from the perspective of astrochemistry, abundances of various molecules, depend very strongly on the density of the gas, because the reactions depend on density. So the idea is, if turbulence induces density fluctuations and the density affects chemical abundances, maybe we can also reverse the arrows and use observations of chemical abundances to learn something about the density structure of the ISM, and in turn learn something about turbulence in the ISM. And what can we learn? So basically, there are three major directions that we can tell from this kind of analysis. And one is the turbulent driving strengths, the driving mode. By strengths, I mean things like the velocity dispersion induced by whatever drives the turbulence, and the mode, and then the scale of turbulence driving. And this depends on what is it that drives turbulence in the ISM. Is it driven on large scale from the galactic potential of the galaxy, or is it driven mainly on smaller scale, induced by supernova feedback, supernova remnants, or maybe even smaller scale from the gravitational collapse and star formation inside molecular clouds? Now, why can we learn about this stuff? Because the turbulence strength will determine the size, the magnitude of the density fluctuations, whereas the driving scale will determine the length scale of the density fluctuations, both of which will affect the chemical abundances in the clouds that we then observe. Okay, now to go through a more qualitative model, to use this idea, what we do is we run hydrodynamical simulation, basically MHD boxes, where turbulence is driven on some scale. This is the first parameter here, the driving scale, and with some magnitude, with some intensity, which is parameterized by the Mach number, sonic Mach number of the turbulence. So these are the basic important parameters for this numerical model. The hydro simulations gives you the three-dimensional density field shown here in 2D. And then we use this as input model for calculating the chemical abundances of various species. In this study, we focused on this HH2 and this more esoteric molecular ions, OH+, H2O+, and argonium H+. Argonium H+ was just detected in the ISM a few years ago. And these specific ones are quite sensitive to the density fluctuations, so they may be good probes of the density field and the turbulence. Once we calculate the abundance of all of these, then we can compare this with observations and use the observations to constrain these two parameters, driving scale and the sonic Mach number. So in order to be able to do that, we have to run not just one simulation, but several with different turbulent parameters. So we run 2 combinations of driving scales and 6 combinations of Mach numbers. And then we calculate all the different abundances. So now we have H, H2, OH plus, and H2O plus, argonium H plus, all this. So we have 30 boxes. For each box, we calculate the column density of each of the species. And then we have probability distribution functions for the column densities. So basically, we use statistics. We compare the PDFs in the simulations to the PDF in the observations. So let me start with some simple result before I go to the full result, just to illustrate the effect of these 2 parameters, the driving scale and the sonic Mach number. What does it do to the chemical abundances? So let's just look at the H1 as an example. So here I show a simulation, the projected column density, the integrated column density of H1 through one of the simulations that have a Mach number of half, so it's subsonic. And what you can see is there's some variation in the H1 column density, but they are not large. And that's because for subsonic turbulence, the density is incompressible. There's small density fluctuations. And so the H1 column density is almost the same for all different lines of sight. However, as you increase the Mach number, you increase the amount of the strength of density fluctuations, and then you have much more also fluctuations in the H1 column density between different lines of sight. And that's the PDF that becomes much wider, the PDF of the H1 column density. Now, what's the effect of the driving scale? What I showed before, this was for large-scale driving. So the density fluctuations also have large scales. However, as we decrease the driving scale, say going from galactic scale driving to supernova to cloud scale driving, the size scale of the density fluctuations also becomes smaller and smaller. So now in the box, as you go into the box along line of sight, you have many, many density fluctuations along line of sight. Now as you integrate along the line of sight, because that's what we observe, integrated quantities, column densities, you basically, the positive and negative fluctuations kind of cancel out, add together, and smooth out the PDF. So the PDF become narrower and narrower as you decrease the scale of density fluctuations. You can call it destructive interference, if you like. So basically, to summarize these 2 points, the dispersion of the PDF of the column densities of various species, here I talked about H1, but the same we see also for the other species, increases as we increase the Mach number, because the intensity of fluctuations increase, and also as we increase the driving scale, as the density fluctuations become more coherent along the line of sight. So now we can take these simulations and apply them to observations and actually try to constrain the parameters of turbulence in clouds. So first of all, in these 3 lines, I show 3 models, just for simplicity, not the whole set. The first one have small Mach number. And what you see here in color, if you ignore for a second the points, the color is the probability distribution functions of argonium H plus, OH plus, and H2O plus. And you see they're quite narrow. So these 3 bands as 1, 2, and 3 sigma of the PDFs. So they're very narrow because small Mach number means small density fluctuations, as we saw. Then as you increase the Mach number, but this is still small driving scale, the PDFs become wider, but they really become very wide only when you increase both the Mach number and the driving scale. And now the points here are observations from Herschel in the galaxy of these 3 species. And what we see that really, well, the match is never perfect, but the first and second, in the first and second cases, the dispersion in the observed quantities is much too large compared to theory. And only in the third model we are able to reproduce the observations. So basically, the takeout is that you need large Mach numbers and large driving scales to reproduce the observations. So we can constrain turbulence with chemical tracers, but there are, of course, as always, several caveats. Oh, we're here in the US, so I should say maybe a future prospect. So the future prospect is I want to add time dependence to the chemical models, which are currently assuming steady state. This might be important as turbulence processes are quite fast compared to some of the chemical reactions. Then non-isothermal hydrosimulation might also play a role. Fluctuation in other quantities, such as the cosmic ionization rate in different locations, may also induce variations in the abundances. And I just, in 1 second, want to advertise my new paper that just uploaded to arXiv, where I suggest a new method to constrain the cosmic ionization rate in cold clouds based on lines from H2, raw vibrational lines in the infrared of H2. So this is a new idea, not tested yet. No one ever, almost, maybe there was 2 instances, looked at cold clouds in the infrared to search for H2 lines because no one expects to see them because they're cold. But I'm saying maybe we can see them and constrain the cosmic ionization rate from this. Finally, if all this is checked and we do all this, we might use observations of chemical tracers to learn something about turbulence in the ISM. Thank you.
One thing that you didn't mention is gravity. Is gravity, can it be ignored in the context of the effect on the chemistry?
Yeah, so it's a good question. Gravity, I think, plays... So for this, for example, it's important to choose the right molecular tracers. Because if, for example, you go to CO or to tracers of more dense gas, then you'll more likely be affected by gravity, and then you need simulations that also have this. But here this is another reason why we concentrated on these strange molecules, OH+, HO+, because it's known that they are more prevalent in more diffuse gas, which is less susceptible to gravity.
Another feature of these higher Mach numbers is that it not only affects the density, but behind these shocks you have heating, and that affects the chemistry. How do you deal with that?
Yeah, so this is point number 2, I guess. So right now, so there's many simplifications to the model, of course, right now. We're still in this process of learning each of which of the parameters, what's the effect. So we assume still either thermal, which is wrong. So we don't have all this. But yeah, I hope to do it in the future years.